Tulips!
Come on, Bergman!
Tulips! I love my tulips!
So we've gone from kazoo
Hi, Mr. Sams. What are you doing here today?
Kazoo to ukulele.
Well, yeah, I got this ukulele. I've been
my
thinking about
goodness.
learning how to play a new instrument. You didn't like my kazoo.
No, you know, that wasn't that
Doesn't
great.
it sound good? Listen, real careful.
Well, the fact that there's only 2 strings on the ukulele is...
Oh, does it need 4?
Yeah, you know, it probably needs 4. That'd probably help you out a
Oh.
lot. But,
I thought this sounds good. This is oh, man, this is the
Cheer.
perfect noise. No?
yeah, noise. That's
Sound! Music!
Alright, my little frowny face is crying. Alright, we should probably do some chemistry, right?
Yeah, probably
Don't
should do
waste
some
our time.
chemistry.
Alright, well,
maybe I should keep that day
again,
job.
yeah, don't quit your day job. Keep doing chem. Alright, so last time we talked to you about naming compounds and writing formulas from those names. We also talked about writing and balancing chemical equations. Now, the reason we do all that fun stuff is basically so we can do stoichiometry.
What'd you call that?
I called it stoichiometry. Now,
Stoichiometry.
yeah, everybody say it together just like you did last year.
Stoichiometry.
Yeah, just like that. Alright, now. We're also going to use dimensional analysis to solve it. That's the format we're going to have you do. That's the whole railroad tracks thing. You guys did it all year last year. We just think it's a great way to solve a problem. All right, so Mr. Bergman, talk us through how we do stoichiometry problems.
Well, you guys have the rules sitting in front of you, so I don't know that you need to spend too much time going over this, but you're going to start with the balanced equation, write underneath what you know, place a question mark, what you don't know, and then use dimensional analysis.
I'm sorry, what did you start with there again, Mr. Bergman?
You always start with a balanced chemical
Are you
equation.
telling me I can't do stoichiometry without a balanced equation?
No, you cannot.
Okay, so make sure you always have your balanced equation before you get started. Don't try to do anything in chemistry without a balanced equation.
So here we have an equation. And so, do we have a balanced equation, Mr.
I don't
Sam?
see a balanced equation.
I
think we
do
might
not
have to
see
make
one either. So I think I better start with a
balanced chemical equation.
So I have hydrogen gas, and of course hydrogen's gas formula is H plus...
Wait, Mr. Bergman, it says hydrogen gas is formed.
Oh, it is formed. Okay.
Is formed tells me that's going to be a product,
oh, so
not
I did
a reactant.
it wrong.
Yeah.
Okay, fair enough.
Putting the cart before the horse.
So that'd be an H. Okay. And it's formed
Mr. Bergman.
What?
Hydrogen gas is not just an H. It's one of those Magnificent Seven or Brinkelhoff elements, as we sometimes call
that's
them.
right. He's one of those H2 guys.
It's a diatomic
I knew that.
molecule.
I was testing you. Okay.
Yeah.
All right. And then we've got calcium. Symbol for calcium, of course, is Ca. And it reacts with sulfuric acid. If it's an ic acid, it came from a...
8 becomes ixosulfate, which is SO4.
Now, when you do that hydrogen, that'd be hydrogen reacting with sulfate, ladies and gentlemen. And that's SO4 2 minus, or negative 2, and H positive, so that'll be...
H2, SO4.
And we make hydrogen gas. Wait a second. There's no calciums on this side.
There's got to be something else. Now, you've got hydrogen gas coming off, and you had a metal combining with an acid. That's probably going to be a single replacement reaction, looks like.
So you're going to have to put the calcium. You see, the only thing left over is we've got some calcium. You see the hydrogen is here. That's from here. And we've got calcium and we've got sulfate. But I've got to figure out the charge of the calcium.
Calcium is always going to be +2 because it is an alkaline earth metal, which always get +2 charges.
When you put these two together, the charge has to add up to...
adds to add up to 0.
Yeah, well, that last time. Yeah, I remember that. So calcium sulfate is CaSO4.
Because +2 and -2 equals
0.
There it is. So we have a balanced equation now.
Oh, wait. Are you sure it's balanced?
Oh, I didn't even look. Yes, it's balanced.
Actually, folks, ladies and gentlemen, this is a balanced 1-to-1-to-1-to-1 balanced equation. Now we have 13.5 grams of calcium. I'm going to rewrite this because I need a blank screen. So I've got calcium plus sulfuric acid, all 1-to-1 ratios, right, ladies and gentlemen? It makes H2 plus calcium sulfate. And we had 13.5 grams of calcium.
Yep, 13.5 grams.
So now I'm going to write down what I know underneath what I know. I want to convert to...
liters of hydrogen gas. Now, one thing, it doesn't give us any sort of conditions. It doesn't give us a pressure or a temperature or anything. So it's a pretty safe assumption that this is going to be at STP. Normally it'll tell you that. It'll say at STP. Or
we forgot it.
Or it'll give you some temperature and pressure. Since it's not there, just go ahead and assume STP for today.
So now you just do dimensional analysis, ladies. 13.5 grams. Now, very important. Did I write 13.5? No. I wrote 13.5 grams. And I must say calcium. I don't say of, but I see grams Ca.
Yep.
Put that over 1. Now I do the whole railroad tracks things. I need to convert to what first now?
We want to go grams to moles. The very first step, just about always, is going to be convert what you know into moles. And the way we go from grams to moles is we find the molar mass of something, or the atomic mass.
So you look up on the periodic table and you find that number is 40. You know, on AP, I've been thinking about this, guys. I think we're going to say 40.1 on this. I want you to take 1 decimal past. Last year in regular chem, we did not do, we just ran the nearest whole. We're going to have the nearest 10th here in AP Chem land.
One general rule you can use as far as significant figures go in AP chemistry is if you use 3 sig figs for everything, you're going to be okay. Because on the AP test, you can be within 1 significant figure, and you still get credit for sig figs. And pretty much every answer on the AP test is going to have 2 sig figs, 3 sig figs, or 4 sig figs. So if you just have your answer have 3 all the time, you hit it on the money every single time.
Now, side note, ladies and gentlemen, are my grams of calcium, I'll change the color, grams of calcium cancel. Now I want to get what do I want to get to go away, Mr. Sam?
We want the calcium to go away and to become hydrogen gas.
So
and the way we do
moles
that,
of
Ca in the bottom,
calcium,
because it wants to go away.
And then I'm going to say moles of hydrogen. I'm changing colors, ladies and gentlemen, because, of course, I have a new chemical here. Now, the mole ratio, this is from the balanced equation. This is 1 to 1 to 1 to 1. This is a very easy mole to mole ratio. This is 1 to 1. But now, my moles of calcium can change. Got that? And now, I'm going to convert to liters of STP. We're again assuming we're at STP. Then I can say, on the bottom, the moles of hydrogen is equal to the liters of hydrogen. This is the gas, so this is 1 mole is, what do we call this number is?
That is 22.4 liters, because any gas will occupy 22.4 liters if you're at STP and there's 1 mole of the gas.
The moles of hydrogen cancel, and now we get our calculator out.
We get the calculator out.
And again, you take 13.5, you would divide by 40.1, and then you would times it by 22.4. Ignore the ones, of course, and that would give you the answer. And the survey says 7.5, actually the calculator, not the survey, says 7.54, and the unit that's left over is over here on the right, liters of hydrogen. Okay? Now, our second problem is similar. We have another chemical reaction. So, balanced equation, we have nitrogen gas reacts with oxygen. So, I got to get on the right side of the arrow.
Yep.
So, I'm going to do the arrow right here. So, nitrogen gas will be in. So, I've got the N, and I need to react with the oxygen. That's the O. And that makes nitrogen triiodide. That'd be N. Trioxide, O3, right?
Okay, Mr. Bergman.
Yes.
Your N and your O there again.
Oh.
Those are more of those Brinkelhoff elements.
Oh, that's right. I need a
2
here in 2 plus O2. But Mr. Sams, that doesn't balance now.
I know, but that means you'll have to balance it.
Oh, yeah, I guess I could balance it, yeah. Okay, like you said last time, most complex compound is the O3. We kind of have a 3 and a 2 here, and so we need to put a 2 in front of NO3 and a 3 in front of the O2, and that kind of gives us the 6 and 6.
Yep.
And the nitrogen actually is balanced that way.
Beautiful.
So I'm going to go write that on a separate screen. All right. Plus 3O2 makes 2NO3.
Alrighty, there we
now,
go.
Now, what do I know, Mr. Sam?
It says how many molecules of oxygen are needed to make 5.5 liters of... Can you go back to the previous slide real quick, Mr.
I
Bergman?
think we have a typo.
We have a typo, a discrepancy in our... Oh, nope, not a typo. Mr. Bergman just wrote it wrong. It is
dinitrogen trioxide. Mr. Bergman is totally making mistakes here. I did that on purpose to test you, Mr. Sams, and you didn't catch me. So we got to rebalance this equation.
Yes,
dinitrogen trioxide.
All right.
So this is going to require a...
I'm still going to say we go with the 2 and the
3.
3, but that's just going to change this guy over there in the front. There you go. Okay, let's try this again. We want to know how many molecules of oxygen are required to make 5...
molecules under the O2, question mark.
How many molecules of those do we need to make 5.5 liters
of N2O3.
Of N2O3 at STP? Now this time we remembered to write at STP.
So I'm going to convert 5.5 liters of dinitrogen trioxide, and I'm going to then convert to liters of nitrogen trioxide. You got to write now, guys. If you forget to write the N2O3, that is called a naked number.
Yes, we don't like naked numbers. We like them fully clothed.
Put your clothes on. It is ugly. If you have ugly clothes, must have clothes on always. Okay, where are your clothes? All right, what number goes on the bottom?
22.4 liters per mole gas.
22.4, I think is how you say it in Spanish. I may be wrong. All right, so liters of dinitrogen trioxide goes away, and now I must convert to mole-to-mole ratio, right?
Mole-to-mole ratio, yes.
So I can say moles of N2O3. Now the number in front of N2O3 here is a 2, a 2, and in front of moles of
oxygen, O2.
Oxygen, and this of course is a 3. Notice I'm changing colors. That's on purpose because now I've moved to my secondary chemical. And now I want to go to molecules.
Yes, moles to molecules. Okay, don't forget.
1 mole O2.
Molecules are individual particles, therefore we need to use Avogadro's number, 6.02
times 10 to the 23rd. So in my calculator, I'm going to type.
You're going to type
5.5 divided by 22.4 times 3 divided by 2 times 6.02. Now don't forget, folks, you're going to push the E button, 23. It's actually the EE button, but it's going to appear E on the calculator, and you probably get quite a number.
Now this calculator is giving me a very strange readout, but it's going to be 2.22 times 10 to the 23rd power.
And that would be molecules, no nakedness here, of oxygen.
I need to change. Calculator's being funny.
All right, then it looks like we have an additional problem. We've got calcium carbonate. It's going to decompose. Now, what does decompose mean?
Decompose breaks down into the stuff it's made up of.
Right,
just
so
like
calcium and carbonate, you have to kind of like do the charges. Calcium's charge from earlier is a 2 positive, and carbonate is a
2 minus.
2 minus. So that's CaCO3, and it decomposes into
calcium oxide.
Calcium oxide. Now I know the charge of calcium is 2 positive, oxide is 2 negative. When we put those together, that's simply CaO. Positive 2 negative adds up to 0, plus a common gas.
A common gas. Well, I see some carbonate there, which is CO3. I know that there's a pretty common gas that looks like CO2.
And that would be the answer.
Carbon dioxide.
And folks, I'm not going to spend too much time, but this is already balanced. Okay? So you get that idea. So we've got the calcium carbonate. I'll get a blank screen. Goes to calcium oxide plus CO2 gas.
All right, and we got 45.5 grams of calcium oxide.
45 point what, Mr. Sams?
45.5 grams of calcium oxide is formed from how many liters of gas? I'm sorry, if that many grams is formed, how many liters of gas is also formed? So we want to know liters of CO2. How many?
Assume that's an STP.
I'm going to assume that's STP.
So, folks, this is probably, you may not need to do this example because we're, I'm going to try and go fast. 45.5 grams of CaO, and I'm going to say grams of CaO.
So that's going to be 56.1 if we really want to get.
And then that will be 1 mole of CaO. In the 1-to-1 ratio, 1 mole of CaO is equal to 1 mole of CO2. And then I'll say 22.4 liters of CO2 to 1 mole of CO2. When you get the math, it comes out to be...
It is 18.2.
18.2 liters of CO2. So probably we overdid that one. Oh well, sorry.
Oh well.
Okay, now we want to move to limiting reactant problems. So you may want to just reread these rules, but basically convert all the reactants. Actually, this is a different method than we taught.
That's right. Last
year, sort of an advanced method, ladies and gentlemen.
Yeah. Last year we taught you to convert everything, both reactants, to something in the end, and
particular product,
and the smallest one won. And you can still do that if you want, but we're going to show you a way that kind of saves you a few steps here.
So you're smart enough now to know that you can save some steps, and we'd like to show you that. So then you're going to divide each number of moles by the coefficient in the balanced equation. We're assuming we have a balanced equation. And then the chemical with the lowest number of moles is the limiting reactant, and then you'll use the limiting reactant for all further calculations. So we'll do some examples. That's always the best way to do this. Okay, it's coming up here. All right. All right, you have this here. I'm going to have to, of course, go to blank screen. There's not enough space.
Yep.
So we have the paper in front of us as well.
All right, so first thing we need to do is write a balanced equation. That's part A. We have iron.
Symbol for iron is?
Fe. It's reacting with chlorine gas.
What? And it makes what?
Brinkle.
Oh, coal. Coal off. Okay, gotta have that too there. Okay, good.
And it's forming iron 3 chloride. That's iron with a Roman numeral 3 after it, which means it has a plus 3. No, Mr. Bergman, it does not mean there are 3 irons.
Oh, that's right. It's the
charge. It's the charge of the iron.
So, ladies and gentlemen, of course, that's FeCl3. Fe is positive 3, chloride minus 1.
And we need to balance that equation. Now I see a 2 and a 3 on the chlorine, so let's just go 3 and 2, make them both 6. Throw a 2 in front of the iron, and we're good to go.
All right, now what do we know here?
All right, now next question says, what is the limiting reactant? So to do that, we start with what we know. We have 114.0 grams of iron, and we have 252.7 grams chlorine gas.
So what we need to do, ladies and gentlemen, is just convert to moles, divide by coefficient.
Correct.
So I'll do the iron first.
All right.
So I'm going to take 114 grams, I won't put the 0.0, of Fe over 1, and then I'll say 50, now it's 55.8, I think. Yeah, 55.8 grams of iron from the periodic table is 1 mole of iron. And what does that come out to be, Mr. Sams?
That is 2.04.
And then that's moles. Why don't you go ahead and divide by the coefficient? The coefficient in this case is a 2 from up here.
So that gives us 1.02.
Yeah, 1.02. So just kind of keep that number in your brain. And then for the chlorine, I'm going to say 252.7 grams of chlorine gas, Cl2 now. Now the molar mass of chlorine is not 35.5. Or it is 35.5.
That's just for Cl, but we have Cl2,
you have to
so
double
it's going to be 71.
71 grams of Cl2 to 1 mole of Cl2.
And that gives us 3.56 moles.
3.56 moles. Divide by the coefficient, which of course in this case is a 3.
Which is 1.19.
And this isn't really a unit, because it's just, so 1.02 of course is smaller than 1.19, so the limiting reactant is the iron.
Yes.
So actually I'm going to relabel this. So if I've got iron, Fe, 2 Fe's, right, plus 3 chlorines, you will not necessarily need to rewrite this, makes 2 iron chlorides, and this
iron
is the limiting reactant. I forgot. And then actually right now I'm going to write down the number of moles. So I'm going to go back a screen for just a moment. The moles were 2.04 and 3.56. So this was 2.04 moles, and this was 3.56 moles. So once I've converted to moles, I can actually save some steps. You'll see an advantage to this problem. So now
all right, next part, C, says how many grams of iron 3 chloride is formed.
So grams here. But which one do I work with, Mr.
We
Sam?
always use the limiting reactant because that one is going to be used up first. The excess, we've got leftovers, so we don't know how much leftover we have at this point, and so we need to work the limiting reactant only now.
So I'm going to just do a conversion. Oops, I just did something wrong there.
Yep.
I'm going to just do down here. 2.04 moles of iron. I can save a step, and I was not even trying to save a step. That was silly of me. Then I can just convert moles to moles. I can say 2 moles of iron. That's from the balanced equation, this 2 right here. And that's equal to 2 moles of iron chloride. And it wants grams, so I do need to do a gram conversion.
Yep.
So I can say 1 mole of FeCl3 is equal to so many grams of FeCl3. That is just from the periodic table. And so the molar mass is 55.8 plus 35.4 plus 35.5 or whatever.
And I just about had it in my calculator. I had a syntax error. 162.3.
162.3. And so when we just do the mathematics, it's going to be about
331.
331 grams of FeCl3. You see, the beauty of this particular methodology, if you recall back to last year, you would have converted grams of this to grams of this, and then grams of this to grams of this, and taken the lowest one. I only had to do one stoichiometric line after I had done the mole calculations. And if there are multiple parts to this problem, it is much easier to just convert to moles.
Did you say multiple parts, Mr. Bergman? You mean like next part, which says how much
there are more
reagent is left over?
Well, you see, I knew it was coming up because I wrote the question. All right, so... And I'm going to rewrite the equation because I always start with a
balanced chemical equation.
Now, what do I know now?
All right, so we had moles of our things is what we were at a little while ago. 2.04, I believe it was, and then 3.56 moles of Cl2. Now, we want to know how much excess reagent is left over at the end of the experiment. Now, which one's the excess reagent? Well, it's the one that's not the limiting reagent or the limiting reactant. So if Fe is limiting, then Cl2 is excess. Now, we need to figure out how much excess is left over, so we're going to start with our limiting reactant. Again, 2.04 moles of Fe.
Now, it's moles, not grams.
Right.
We get to save a step.
We're
That's a beautiful
there.
thing.
Now, let's figure out how many moles of Cl2 would have reacted with that. So let's just do a mole-to-mole ratio.
So that would be 2 moles of Fe. This is from the coefficients in the balance equation, is 3 moles of Cl2. And since we actually, it asks probably you want to go to grams, we're going to go one more step and go all the way to the grams of the chlorine and then subtract from like 200 and whatever that number was.
Okay.
And then we'll say 1 mole of chlorine is equal to 71 grams of chlorine, molar mass, right?
Yep.
Cl2. And you come up with?
217.
217 grams of chlorine. Now, what does that number represent?
Actually, Mr. Bergen, let's have an extra digit in there. Can we call it 217.3?
0.3, okay.
Thank you.
And that would be the amount of grams that were...
Reacted. That's how much got used up with the iron. So, if we look at the problem, we started with 252.7 grams.
Right, so 252.7 grams.
And we found out that we just needed 217.3.
You only used up 217.3 grams of chlorine, so of course you simply subtract. When you subtract these on your calculator, it's 35.4 grams of chlorine. Less is how much that's left over. Make sense?
Moving on.
Next one, we've got more to do for you.
Do we want to do another limiting reactant problem?
You know, guys, I think you get the idea. I think this is probably excessive.
If you need to practice, do this one. It will help you out when you get to class. But I think in the interest of time, so this doesn't get too terribly long.
Bingo, you are amazing, Mr. Sams. Okay. Yeah. Should I get my harmonica? I mean, my...
the ukulele?
Out?
Let's just move to percent yield.
Okay, percent yield.
I think I might rather do a limiting reagent problem than listen to more ukulele.
Okay, you don't like my voice? What?
No, I did.
All right. Percent yield, very simple problem, folks. You can read these rules. Balanced equation, right amount that you've given. This is similar. The key thing is actually sometimes you don't make as much as you expect to make, and then we have a percent yield. That's probably best if you look at these instructions, and we'll do an example. Nitrogen gas. Nitrogen, I think it's N2.
It is N2.
Mr. Bergman's learning. Reacts with hydrogen, that's BH2.
That's the Brinkelhoff.
And it makes ammonia. Ammonia is, as it says, NH3.
By the way, ammonia is just one you want to commit to memory. And just know that ammonia is NH3. Know that methane is CH4. Just a few of those little simple compounds you just need to know.
When you balance this one, this is a little tricky. I think you guys are getting good at this. This will be a 2, this will be a 3, and this is a 1.
Yep.
Okay, now I've given some information.
All right, it says we have 15.5 liters of N2 reacts at STP to make 30 liters of ammonia. What is the percentage yield? Now, notice that it says it made 30 liters of ammonia. That is, if you did this in a laboratory or industrial setting, and that's how much stuff you actually got out of the reactor. Now, the stuff you always get out is never the amount that you expect it to be. Ever, 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 ever. I don't care how good you are, you will never get a 100% yield. Actually, you might get 120% yield, but that just means you have something unreacted and contaminated and weird, but it will never be perfect. So we're going to call that our actual yield in the that we actually produced, the 30 liters. So we need to figure out how much is expected. What did we theoretically, what should we have gotten? And we're going to do that through stoichiometry. I love that word.
I do too. It's amazing.
Okay. I think I'll name my next child stoichiometry.
I thought you weren't having any more kids.
Yeah, okay, fine, we're done. I'll just rename Zeke.
There you go. All right, so this is just a simple, folks, liter-to-liter problem. Actually, you know, I should show them something. You want a shortcut?
You want the shortcut liter-to-liter?
Shortcut?
Shortcut, because it's all at STP. It doesn't give us any new conditions since they're all at STP.
Essentially, you'll have 22.4, and it would balance. You have 22.4 on top and 22.4 on top bottom, and of course, if you have the same number on top and bottom, they will cancel. So you can actually use the mole-to-mole ratio. You can say 2 liters of NH3. It only works with liter-liter. Won't work with gram-to-gram.
Only works liters-liters, and if it's all at STP. 1
liter of N2, and then boom, your liters of N2 cancel. I can do this without a hard brain head or whatever it is.
A what? A hard brain head?
I don't know. I can do it in my head, okay? So this would be 31 liters of ammonia.
There you go.
So that's how much we're expecting to get out, or usually it's called the theoretical amount.
So that's 31 liters, and how much did we actually produce according to the problem?
30.
It said we made 30.
So I'm going to take 30 over 31.
So actual over your theoretical times 100.
So 30 over 31 is 90-some%.
That's 96.8% or 97%, we can probably call it.
Yeah, probably can keep digits, 2 digits, so 97%. Not terribly difficult. These problems are elementary. All right, percent composition.
Percent composition? Click resume.
Hey, we're back.
There we go.
There we go. We were afraid we'd lost it all, and we were so good.
Yes.
Especially me. Don't you think? No? Okay. All right. Percent comp, folks, you guys, these are so easy. If I want to find the percentage of each element in a particular compound, this is well, it's elementary.
It is.
So if I have ammonium nitrate, NH4, in O3, we need to find the total molar mass, which will be 2 times 14, that's the nitrogen compound, plus, I see there's a nitrogen here and a nitrogen here, 2 places, plus 4, that's my hydrogens, plus 16 times 3 for the oxygens, and I get a total of 80. So the molar mass is 80 grams per mole for ammonium nitrate. So to find the percent composition, I take the nitrogen, the hydrogen, and the oxygen. The nitrogen will simply be 28 divided by 80 times 100, and that gives me 35%, because there were 28, 2 times 14. For the hydrogen, that will be 4 over 80 times 100. That will be a much smaller percentage. That will be simply 5%. And the oxygen, we could actually subtract from 100, or you could just take 16 times 3. You could do this, by the way, over 80, which is like 48, times 100, and that should be the remainder, which is 60%. So in this particular compound, 60% of the compound is oxygen.
By mass.
By mass. 5% hydrogen and 35% nitrogen. This is a very elementary problem, and you'll go, oh yeah, I remember that. We have one last thing. Do you ever make errors, Mr. Simmons?
No, never.
Okay.
Especially when I play the ukulele.
Yeah, well, you must be as good as I am,
Oh,
because
yeah.
I don't make
Oh,
mistakes in
yeah.
that. So we have this error equation, and of course you've remembered the error: observed minus actual divide by actual times 100. You know, technically, by the way, folks, you should put parentheses around this, because it messes up if you try and do it in the calculator that way.
That's right. Order of operations.
Order of operations.
By the way, this can be a negative number. That means you got below the value you should have gotten, or it could be a positive number.
So let's say I'm doing a particular project, and I'm doing a particular, I'm finding the density of a compound. So I did an experiment, I found the density of gold, doing some particular experiment. And I find the density of gold to be 18.8 grams per milliliter. I can then look up in a table where somebody has measured accurately, super duper way, amazingly accurately, the density of gold. And if I looked it up in the table, it would be 19.3 grams per milliliter.
You just know that off the top of your head?
I do.
Wow.
I do know that off the top of my head. I am amazing.
You are, in fact, two amazings.
Two amazing at the same time. I can even spell all the time perfectly. So, so if I got 18.8, I did not get the correct answer.
No,
the
you
correct
did not.
answer, the accepted answer, is 19.3. So I'm going to say 18.8 minus 19.3, parentheses, divided by 19.3 times 100, and I get a whopping negative 2.6%. Now, why am I saying a negative for 2.6%?
It's negative, Mr. Bergman, because your number is below the accepted value.
Now, let me just say a quick note to some of you who are watching kind of in internet land. If you're doing a percent error, oftentimes you'll see the equation written as an absolute value right here, and then it would just be 2.6%. It is a 2.6% error, but I prefer to leave the sign, the negative sign in this particular case, to tell me that the number is low.
Yep.
So that's why it's there. If you're watching this in internet land, or our students who maybe go out to the world and see this as the absolute value, they're both correct, but ours tells us more. If it's positive, then we say it's a positive percent error.
Oh,
Oh
my goodness. Okay, you're probably going to want to just hit stop right now. This is where it's done. Yeah, I'm just going to stop it now. Bye, guys.